Hello, I'm Ezekiel Markwi, a graduate student at the University of Florida in the Electrical and Computer Engineering Department. Today I'll be presenting to you my final project in image processing and computer vision, taught by Dr. Wu. The title of the project is Image Change Detection Techniques. So one may wonder what change detection is. This is the ability to be able to detect changes in any two selected images of the same scene. You can see, for instance, in these two images that there are some changes in the clock as in the minute hand moving and also the stapler opening. This kind of changes are actual changes caused by object movements, and hence uh, the name object movements, as you can see, represented by M. Other changes caused by changes in illumination and light intensity as well as reflections, as you can see here in image 1, are called spectral reflections, represented by S. And also you could see here variations in appearance on the banana from comparing image 1 and image 2 through the spots that are shown and the discoloration. You may be wondering the importance of change detection. Actually, this is a very important technique, and it's applied in so many fields. uh, these images are images captured by the Kepler telescope of for NASA, and it's used for remote sensing to determine some astronomical changes. Actually, this telescope has helped in finding or discovering new planets, some of which are Earth-like, and it can help in knowing whether life exists on some planets. How this telescope works is that it detects changes in light intensities, such that whenever a planet passes in front of a sun, it reduces the amount of light intensity captured. So based on the variation of light intensity, they can tell uh, whether a planet has passed before in front of the sun and where the planet is in relation to the sun. So you can see within these two images that these two images that this object, tiny black object here, is the planet, and this is very critical as billions of dollars are spent on this project to be able to detect life on other planets and the existence of other planets in the galaxy. Image change detection is also employed in video surveillance to be able to see whether intruders are have come to a place, or whether there are any abnormalities in any two scenes at any two standpoints, as you can see in these images. Another application is in the medical field, where you're able to detect growth of cells. And for instance, when someone gets treated for cancer, you want to know whether their cancerous cells are growing or they actually are reducing. You can see in these two images here that there's this black spot, which is a change, and this image change detection shown here shows you the change that has occurred. A doctor looking at this will then be able to tell whether this is a bad or good sign. Um, there are some changes that are there are some challenges that I ever faced in change detection, and that is being able to know which particular change you want to see, and based on that, you can select the right algorithm, or produce or write up the right algorithm. There are also other challenges faced for unimportant changes like changes in illumination, which are often not very important, in many uh, change detection applications. Also, camera movements. When you take a picture or an image at one shot and the camera moves and take another shot, it may look as if some changes have occurred, but that's just because of camera movements. And you want to have the images being of the same alignment so that you can really tell whether any change has occurred by movement of the object. Also, there are some changes that are caused by sensor noise, that is in the sensors of the camera. So to be able to mitigate these challenges I've stated above, some procedures that are often followed. One is the geometric adjustment. Now, what is that? Is that it aligns the coordinates of one image to that of the other image, so that you'll be able to solve the issue of camera movement and hence get one like similar image from the same angle and tell which kind of changes have occurred. Another is radiometric adjustments. This helps in being able to notify the effects of variation in illumination, as well as mitigate uh, changes caused by noise or issues noise generally within images. Stochastic modeling and hypothesis testing is used to actually get the two images together and hence be able to see what change has occurred. So here, there's an example of geometric adjustments. You can see the two images are from different angles, probably by the movement of the camera. Now, what geometric adjustment wants to do is it wants to take this image, for instance, and align it to the angle of this image using its coordinate, the pixel coordinate, such that you'll be able to get both pictures from the same angle and you can actually see whether some actual changes have occurred or not. Radiometric adjustment is an example of variation in illumination. You realize that there's no observable changes in these two pictures, but then there's some change in illumination, which is usually considered unimportant for change detection purposes. In this image, you can see that there's a lot of noise, and to mitigate the noise, you can use the 3x3 filter in the radiometric adjustment to be able to achieve this image that will be used for detection of changes in the image. So my project, I try to focus more on these particular models that have stated the derivative model, the linear dependent detector model, and some predictive algorithms, including the constant, linear, and quadratic models. I've written MATLAB programs for this that would use two images and be able to tell the change that has occurred. Due to how long the MATLAB program takes to run, I want to run it right now, for instance, for the quadratic model, so that I can take you through the rest of the presentation and show you the image that it displays at the end. So when we go into my MATLAB code, which I've opened, I first have to tell where my files are. File 1 representing image 1, file 2 representing image 2, and the output where the image should be placed. So I call find main function and I put in quad mode. You could call, instead of quad mode, you could put in, for instance, M derivative, your linear mode, your linear dependence, or constant mode to be able to tell the change. So let me run this. And whilst it runs, I'll continue to take you through the rest of the presentation. So I took these two images on campus of myself, and the changes that are very critical to me are these two people coming here, the car right there on the street, which you don't see here, and this other person walking here, which is moved further away in this image. You also notice that I'm a bit slanted to the left in this image and a bit slanted to the right in this image. So these are changes that I am looking to see in my models. These images will be changed to gray images and to be resized to ensure that the program runs a bit quicker. So let's start with the M derivative model. How to detect these changes? You first have to be able to take the image 1 and image 2, and what you do is you deduct them, one from the other, and the amount of variation that is seen when it exceeds a certain threshold, you can see a change has occurred. So what you do is you take the whole image and you break it into equal size fixed blocks, and you assign each block six anonymous coefficients. Now, based on this coefficients, you'll be able to find your surface function for the grade level, and you'll be able to then calculate your frame for the particular image. I represent image 1 or image 2. Once you've got this calculated, you can now then calculate your change, and when it is a particular established threshold, you can tell that the change has occurred. This is the final image I got, change section image I got from this model. You can realize that it is not very optimal. There are so many changes that have occurred which I consider unimportant, and this this model is often seen to be less computationally intricate. It's much easier compared to other models. To move on to a linear dependent vector model, this incorporates vector models such that it takes into account the other regions that are close by to it and helps in detecting the change. If a vector is linearly depends on other vectors, then you can use that to determine whether a change actually exists or not. So based on the variation of between two vectors, you're able to tell that there is a change or there's no change. Now, if the variation is equal to 0, that means that x and y are linearly dependent, and when they are linearly dependent, that implies that no change has occurred. But if the variance is greater than 0, then they are linearly independent, which tells that a change has actually occurred. You can see that this is the result I got from running this model, and though it is better than the derivative model, you can realize that there are still some changes that are pretty much unimportant to me, as you can see, because the vector incorporates depends on other vectors within this region. Realize that there is overlapping in areas. This is also less computationally intricate in comparison to the next models I'll be taking you through, but then it is slightly more intricate than the derivative model, and it's a bit more optimal than the derivative model as well. The final models are taking you through the predictive models. This uses second order bivariate polynomial in its function. What it does is you have to find the intensity of a block, values for intensity for a particular block, and fit it onto some established coordinates for the polynomial function. Now, if it's fixed perfectly, that shows that there's actually a change. It confirms the existence of a change, and depending on how well it fits, you can tell whether a change has really occurred or there's a change has not occurred. There are three types of models called the constant, linear, and quadratic models, which I'll be taking you through. So when I ran the program, this added the images I got, and realized that the quadratic model is the best model here, because even though the changes are similar, the whiteness in the quadratic model is much clearer than the constant model, as you can see me showing with the arrow. The whiter it is, it tells that it's really certain about the change that has occurred, and hence the quadratic model is a more efficient model in comparison of the three. I considered other related work, including the shading model. This actually takes a particular pixel points in an image and compares it to another image. It is realized that this kind of model is not very optimal, as it only takes into consideration particular points of the images and compares them, and hence there's a lot of likelihood of it having wrong change detections, or that may be considered as unimportant to the user. Another model I also looked into was a motion segmentation based detection, which was discussed by Dr. Wu in his paper. Now, what geometric adjustment does is like it's also called image registration, and it helps in actually being able to mitigate the effects of camera movements. But then it's difficult to tell whether the camera has actually moved or whether the objects in the scene has moved. So using image registration is a bit difficult, and what the motion segmentation based technique tries to do is it actually focuses on the velocity and direction of the objects in the image, and this helps in being able to tell whether a change has occurred or not. Another work I also looked into was the robust feature-based object tracking, which is using 3D computer vision, etc. And what it does is that it's feature-based, and when it looks at a feature in comparison to other features in a particular area, it tells its motion to that features and is able to help detect what changes have occurred. This is also another paper that was written by Dr. Wu that I read and added to my related work. So before I conclude, I think the MATLAB program has finished running, and as you can see, this is the image that it produced for the quadratic model for the predictive modeling scenarios. In this quadratic model, you can see, as I stated, the white is very clear, showing that the change has occurred. Two people that are coming. You can see probably the car that was there, the man that was moving, and this actually helps you show the changes that have occurred within the two images. I'd like to thank Dr. Wu at this point and thank all of you for listening to my presentation.